With this video, I start a new series on the characteristics of nonparametric statistics. I will say at the outset that many of the characteristics that I'm going to look at apply to parametric statistics as well as nonparametric statistics, but the fact that this is in a video series about nonparametric statistics will motivate me to consider these characteristics with an eye to nonparametric methods. This first video in the series is about the properties of estimators and test of parameters. One of the most important properties that we talk about when talking about both estimators and tests is whether they are unbiased. An unbiased estimator is an estimator that has an expected value equal to the population parameter estimated by that estimator. So if you are drawing samples from a population and you're calculating a statistic and using that statistic to estimate a population parameter, if you were to draw multiple samples and calculate that statistic each time, will the average of those statistics equal your population parameter? And if they will, we say that your statistic or that estimator is unbiased. For example, the sample mean is an unbiased estimator of the population mean. If I were to draw samples over and over and over again, and in each sample calculate the mean, and then average those means across all the samples, that average would be the population mean. Knowing that in the long run we will obtain the population parameter does not mean that we're going to draw multiple samples, but it does mean that we theoretically know that the sample estimator is a good estimator of the population parameter because its expected value is going to be that population parameter. I like to refer to this as many wrongs make a right. The sample median is an unbiased estimator of the population median if the population is symmetric and an even number of observations are drawn for the sample. That's very unwieldy. Not only do we need to know that the population is symmetric, and often when we use the median it's because it is not symmetric, but we have to take an even number of observations in order to have an unbiased estimator. There's a better way. The Hodges-Lehmann estimator is an unbiased estimator of the population pseudo-median. What do we mean by pseudo-median? The pseudo-median is the median of the Walsh averages of two random variables with the same population distribution. If you have been watching the video series in order, you will have seen me calculate Walsh averages using sample data. Well, imagine doing the same thing with population data, with the whole population distribution. The median of those Walsh averages is referred to as the pseudo-median. It actually has some nice properties. It is the same as the median for symmetric distributions, and it's close to the population median for non-symmetric distributions. The Hodges-Lehmann estimator is an unbiased estimator of that pseudo-median. Therefore, by using the pseudo-median, we have a good index for the center of our population distribution, and we have an unbiased statistic to go along with it. Unbiased estimators are important, but so are unbiased hypotheses tests. An unbiased test is a hypothesis test in which the probability of rejecting the null hypothesis is at most alpha when this hypothesis is true, and at least alpha when the alternative hypothesis is true. This means that we have a better chance of rejecting the null hypothesis when the alternative is true than when the null hypothesis is true. You may be saying, well, yeah, and in fact that's what researchers and statisticians around the world say. It is so important to use an unbiased test that you may not have even heard the term before because all the commonly used statistical methods, both parametric and non-parametric, are unbiased. If you have learned a hypothesis test in a statistics course, it is almost certainly an unbiased test, whether or not you were taught that it is an unbiased test. So you can rest assured that the methods we're looking at in this video series fall into the category of unbiased hypothesis tests. Another property of statistics is whether or not they are consistent. If a statistical estimator is consistent with an increasing number of observations, the estimator will converge to the parameter it estimates. That is, if we take bigger and bigger samples, and if we know that our estimator is a consistent estimator, we know that the probability is increasing that the value we calculate with our statistic is going to come close to the parameter that it is estimating. That may sound to you a lot like an unbiased estimator, but there's a difference. With a consistent estimator, we're talking about as the sample size increases, we increase the probability of becoming close to the parameter. With an unbiased estimator, we did not talk about increasing samples. We talked about in the long run across multiple samples, no matter what the sample size, that the expectation of the statistic will be the parameter it is estimating. Both of those characteristics sound very good to me, as they should to you, and indeed, we prefer estimators that are both consistent and unbiased. Another characteristic is that of efficiency. The more efficient an estimator, the fewer the observations that are needed to obtain the same information from the estimator. What do we mean by information? Well, consider a confidence interval. If you have a narrow confidence interval and you have a wide confidence interval, each of them calculated with the same confidence level, which do you prefer? You prefer the narrower one, of course. Why? Because it provides more information. So that tells you something about information. What about efficiency? Imagine that you could construct just as narrow of a confidence interval with fewer observations by using another method. Then that would be a more efficient method to obtain the same information. Notice that I'm using words like more and that I'm making comparisons. This should suggest to you that one of the most valuable aspects of efficiency is that we can use it to compare methods. And indeed, you would be right. In the past videos, I've been looking at many different methods for testing the same hypothesis, and I would like to know which one is most efficient. That is, which one should I use? Should I use the sign test? Should I use the Wilcoxon sign rank test? Should I use the t-test? All this gets into the realm of relative efficiency, and that is such an important topic in nonparametric statistics that the next video series you should watch after you finish this one is all about relative efficiency. The final characteristic that I'm going to talk about in this video is the robustness and stability of tests. When I hear the word robustness, I hear it in two different contexts. First, robustness to violations of the conditions for valid inference. That is, how well is your method providing you the probabilities that you believe it should be providing you if the conditions necessary for valid inference when you use the method are not actually true? For example, suppose you were using the t-test and you set a type 1 error rate at 5%. Is the t-test indeed holding your type 1 error rate at 5% if you don't have a normal distribution of scores? That's a robustness question. If the t-test does well at holding your type 1 error rate at the nominal level or at giving you the power you expected with the sample size that you have, then we would say that the t-test is robust. That would be a good thing, but if the t-test is not robust, then we might want to seek another method. The more technical way I see the term robustness used in statistics is to refer to how a method is influenced by a small portion of the data. And there are multiple characteristics of stability that you could read about in the statistics literature, including tolerance, estimator breakdown, sensitivity curve, influence curve. All of these are different ways to get at the same issue, and that is robustness of the method to influence by a small portion of the data. For example, tolerance is a way to estimate how much of your data could be changed, either through mismeasurement, some type of data corruption, outliers, before it will have an impact on whether you reject or retain the null hypothesis. In fact, we talk about tolerance of retention and tolerance of rejection because these are two different aspects of our hypothesis test that could be influenced by changing some of the data. You may not have heard the term stability or tolerance or any of these others used when you were learning parametric statistics because they're seldom discussed. But in nonparametric statistics, we recognize the value of the tolerance our methods have for having incorrect data due to mismeasurement, due to corruption of some sort, things that occur on a regular basis in research. Yet when we do our statistical analyses, we take the numbers and treat them as if they're correct. This idea of tolerance may lead us to sometimes use methods in which we have higher tolerance, with, of course, consideration for other characteristics that we'll be discussing in future videos, such as the power of a method and the relative efficiency of that method.